I think we often overestimate the expectation the public has for useful applications. The public wants to know what is going on in this research center, and there is an extraordinary curiosity of the public. Lots of people love science simply because it is something they find stimulating and they find exciting. And you see how, the eagerness the general public has to buy scientific magazines, popular magazines. We often wrongfully assume that the public wants practical applications when the public is simply happy to know about the basic science, as long as it is explained in ways that make sense. And this is why it is important for all of us to think of which part of our work we can showcase and explain in the most understandable way. And most science can be explained in an understandable way to non-scientists. What I'm going to talk to you about today is a fascinating topic. Can we predict phenotypes? So for those of you who are not biologists, a phenotype is just a fancy name for anything you can measure in a living human being. Height, color of the eyes, color of the hair. One of our goals is to show that given the genome of an individual, it is possible to predict his or her phenotype. We hope that if we use genomic data well enough, we'll be able to predict what is going to happen to you. One of the most ancient examples we have is Stonehenge. If you look at Stonehenge, what it happens to be, it's just a pocket-sized calendar of prehistorical time. And at the time, it was very, very important to go and to know once a year when spring was coming. It's a very, very old and good example of this urge we have of doing prediction. Of course, the scientists got very, very serious about these predictions. And in the 19th century, it's really in the 19th century it became very, very serious. And the nicest example I can think of is phrenology. You had old guys with long white beards, professors of university, who would go and analyze the shape of your skull and decide precisely whether you were gifted for mathematics or whether you will become a natural born killer. And that was phrenology. The way these guys were measuring the shape of the skulls was very sophisticated, and in fact, when today we do anatomic measurements, we are still using the techniques that were developed in these days. The problem was more that these measurements were correlated with the wrong quantity. And in fact, the 19th century was a terrible time because you may argue, if you look back in the history of humanity, that racism as we see it today appeared in the 19th century. Before the 19th century, nobody liked anybody, but people were not racist per se. They simply did not like anybody who was not from their family. During the 19th century, because of this kind of measurements, correlations were drawn between physical features that could now be measured objectively and other kind of characteristics. And that was more or less the origin of what is called scientific racism. It is something we have to be aware of, that science, if you do it the wrong way, can lead to this kind of prejudice. Right now, as we speak today, it is very obvious that science has not given up on the idea that simple measurements can predict your future. And I'll start by giving terrible examples. This is a 2D, 4D ratio, and it's just an observation that if you measure the ratio between your index and your ring finger, you can usually predict pretty accurately some risks. And it is true that this ratio is, for instance, a very good predictor of your risk of having heart attack and some kind of heart disease. But now, what usually happens is that you see the big headline in the newspapers and they say new 4D, 2D ratio predicting piano playing capacity, aggressivity, and these kind of things. And nobody ever goes to read the papers that are behind. And the papers that are behind are always the same kind of paper. They try to draw a correlation between one quantity, the variation on your 2D, 4D ratio, and another quantity, for instance, your tendency to be very aggressive. And if you go behind the paper, if you go to read the paper that is behind this result that was heavily reported, this is the tendency of aggressivity. So the guys conclude that the finger length ratio correlates with physical aggression in men. The data above is a supporting evidence. I don't know if all of you are familiar with what is a correlation, but in a correlation, you have one quantity that vary and the other that vary exactly the same way. So if it were a correlation, all the points should be nicely aligned. I think this situation is probably the worst that can happen. Of course, if you have the right statistical massaging tools, you always end up with some kind of p-value and something, and you conclude in the paper that you have a correlation. People don't read the paper, they conclude on the basis of the title of the paper that this is correct, and that's it, it's in history. This happens all the time, and this is still happening a lot today. Your capacity to publish correlation that bad is a statement of how powerful a scientist you are. You know, if you can impose this kind of things in a journal, that means you're really, really powerful. There are other examples, and this one is a nice one because it is being very, very discussed this day. It's a paper done by a bunch of economists, and they started trying to link human genetic diversity with economic development, reaching the conclusion that there is a high correlation between genetic diversity and economic development. This is a kind of situation where, you know, people are used to say, one can fit an elephant in the model. You will always find a way to model this data. This is an extremely dangerous result because this is taking us back to the 19th century where kind of pseudoscience is establishing pseudo results that could have a real consequence on our daily life. With this kind of result, the society may tell you who you can marry and who you cannot marry. And it's a terrible result because it means that the state can tell you, oh no, you cannot marry this person. This will decrease the genetic diversity of the population. You'll have to marry that person instead. So one has to be very, very careful with these things. Genetic variation is probably one of the most sophisticated traits we can measure in human. Thanks to the very, very high throughput technology, we now have the capacity to sequence the entire genome. And everybody in this room, the 200 people in this room will have their genome sequenced by the end of the decade. Actually, the truth is that the question is not whether all of you will be rich enough to have your genome sequenced. The question is whether all of you, anybody in this room, will be rich enough not to have his or her genome sequenced. This is how serious these things have become. The ideal situation in that case is to go for 23andMe. So we have people in the audience who have gone to 23andMe, and it told them quite interesting things. So 23andMe, you just spit in a tube and you send it by FedEx, and now it's quite expensive. It used to be cheap. How useful is 23andMe? Well, it's very disappointing. Whole genome sequencing fails to predict risk of most common diseases, which simply means that there are a few rare diseases, and like some rare types or not the most common type of breast cancer, for instance, that are highly predictable with this genomic analysis. You know, colon cancer as well can be highly predictable. But most of the conclusion, of the medical conclusion you could draw from 23andMe are pretty useless because these are very, very tiny risks, and sometimes there is no risk at all. So some people are now getting sick because they receive their 23andMe and they have the iPhone application and they keep watching every day if they have discovered a new, because you know, they do all the variations in your genome and then they keep updating all the illness that can be associated with the variation. But usually they call this an odd ratio. That is the probability you have an increased chance of having the disease. This odd ratio is usually very, very low, even for the strongest marker. It's 1-2% more chances. So if you just read, you know, the result, it says you have more chances of having colon cancer or having Parkinson's disease, you get very, very worried. But in reality, it's very, very tiny. And overall, as we speak, these things are changing all the time because more and more data is being gathered. But as we speak, these things are not so informative. It's much more interesting if you want to know about your ancestry, if you have, this is fascinating, for instance, for Americans, for people coming from countries that have a complex history, a complex migration history. It's a fascinating tool. It is going to tell you, and it is going possibly to reveal things you did not know. Now, there is a very nice story that shows the limits of our current capacity to do genetics. This is the height prediction. So if you go to Facebook and you look at the height of all your blood relatives, and you try to average this to get an idea of your own height, you'll get your own height correct at plus or minus 5 centimeters. And this is something that had even been worked out in Victorian era. You know, they knew how to predict people's height quite accurately. Now, if you do the same with 23andMe, and you use all the loci that are supposed to control our height, so I think there are now 180 that have been reported, but if you use the 56 more informative, you get your height plus or minus 30 centimeters. You know, this is quite dramatically low, especially when we know that height is really a genetic trait. But the bottom line is that we don't really know where it's hiding. So One of the problems we have here is that height, as we describe it, is only one number. And one number that is in fact describing something that can be extremely complex. These two nice ladies have roughly the same height. But if you look, for instance, at their belly button, or if you look at their tights, you can see that anatomically they are quite different. Hoping that you can describe this variety with variations in a single gene is absolutely hopeless. And in fact, in this specific case, we would expect, because they have the same height, that all the genes controlling this height are in the same state, have the same variations, which makes no sense when you look at the physical variation between these two girls. And the problem is that high genes are all over the place in your genome. The bottom line here is that one single number is not enough to describe such a variety of phenotype. To give you an image, if I were recording the height of everybody in the world, and if I were putting this height into a USB key, you know, that would hold in this tiny USB key, 8 grams. If I were doing the same, and if I were recording the variation on the 108 eye genes of everybody in the world, I would need about 200 USB keys, which means that I will have about 1,600 kilograms of USB keys. So the argument that I'm going to propose here is that we need more informative ways to measure phenotypes. How can we make phenotypes more informative? Well, here is an example. So this one is easy. So every morning you go to your We Play station, and your We Play station measures your weight. Why is this so interesting? Well, as you all know, there are illnesses where the first sign is a rapid loss of weight. It might be that it will take some time for you and your family to realize that you have lost some weight. But the machine may recognize very rapidly a pattern that is characteristic of the way one loses weight when developing one of these illnesses. And the machine may be connected to the internet, to your GP, to your hospital, and may immediately tell you, issue a warning that you should go and get a consultation because the way you're losing weight is not normal. When you want to use this kind of data, you need to do something we often do in biology. You need to do some kind of modeling. It simply means describing the data in a mathematical way. You know how to compare one number, but you don't know, and I don't know, how to compare these profiles. It's much more complicated to produce a meaningful comparison. This is why the modeling is important. Now, we are applying this in collaboration with Mara Diersen in a formidable machine that has been developed by PanLab. And it's a machine that makes it possible to record everything a mouse is doing, second per second, for a duration that is up to 6 weeks, actually. And so you know everything the mouse is drinking. You can give it alternative things to eat, like chocolate and normal food. And you can see what is the effect on the way the animal is behaving. The recordings themselves, they look, so this is Mara Diersen who is producing this data, and that will be your typical animal. So each line, you know, it's just time going through, and now the animal has started eating. It will be eating during about 5 minutes, and then it doesn't eat anymore, and then it has another meal. What you can see here, and we know this, mice are nocturnal animals, and so this will be the normal behavior, the standard behavior of a pretty normal animal. When you give to this animal chocolates, it's one of the best models we have for heroin and for addiction to a hard drug. And so this is called a free choice system. The animal has been given the choice between standard food and chocolate. We know how much chocolate it is eating, and we know how much standard food it is eating. And it is not eating so much chocolate. It is eating quite a lot of chocolate, but not so much, and not only chocolate. But what is interesting here is that as time goes by, we see that the way this animal is eating is changing. This animal here that is given chocolate starts more and more often to be eating during the day. While the normal animals are having long meals, this one is going like this, is having little snack all the time. So it's a bit like you and I going to the fridge every 5 minutes. You know, there is something delicious in the fridge, like I don't know, some chocolates or turon or whatever, and you say only one little bit, and you eat it, and then you go back, and every 5 minutes you find yourself going to the fridge. And that's exactly what is happening with the animal here. You see from time to time the animal is behaving normally, as you would expect. And then from time to time, it starts going into this snacking mode, this sort of obsessive mode. We call this loss of control. It is losing control. We need need to quantify how fast this addiction is happening. Maybe we will find ways to prevent it. How are we going to be able to distinguish between these abnormal meals and these normal meals? Well, it's very much like in each mouse we had two animals. We have a sort of Dr. Jekyll and Mr. Hyde, with a mouse that is eating normally, and suddenly it has a change in the brain and it starts eating in a compulsive pattern. And we need to figure out who is who at any time. The truth is hidden from us, and in biology we have a very, very powerful way to do these things. It's called hidden Markov models. It sounds like a very technical name, and it is referring to a very technical mathematical way of modeling the signal. But some of you are using this every day, because the voice recognition software that we use hidden Markov model. So in a hidden Markov model, the idea is that the model will figure out what has been emitting your signal. When you talk, the sound is not hidden, and when your phone hears your voice, it receives a signal. It's figuring out exactly which word is producing the sound waves that your phone is receiving. Now, in the case of the mouse, it's much simpler. We only have two words. We have one that is generating normal feeding patterns and one that is generating abnormal feeding patterns. We'll be able to label every observation we have as to whether it has been emitted by the mouse in a compulsive state or if it has been emitted by the mouse in a non-compulsive state, okay? You can quantify things, you can measure, and that's what we call modeling. Then we can do our own correlations. We can see the emergence of abnormal meal patterns long before the animal is overweight, and we can draw conclusions. This has huge implication for human health, because if you can do predictive, this means you can prevent, and maybe you can correct in time. Now, how will we obtain this data in human? These are all the smartphones we all have in our pocket now. This one is special. This one has been made by an Israeli company, and it's kind of the most sophisticated. With that stuff, just putting it on your skin, you can really follow your body fat, your heart rate, your stress level, your blood saturation, your blood glucose. So it can follow in real time any kind of parameter or most of the useful parameters. And this is, for instance, a paper that has been published a while ago about using GPS-enabled cell phones to track the travel patterns of adolescents. It's probably the dream of any parent. Of course, this is meant to be correlated with obesity rate. And no surprise and no prize for guessing that small traveling patterns means higher obesity rate, of course. Lots of people are thinking about these things and applying them in global, using GPS system in health research, and how the data is going to be correlated, collected, and processed. This is, for instance, another example I found on the web about a blood glucose meter that is connected to your mobile phone and that is talking with the cloud. And in that case, it's a medical cloud trying to figure out how to optimally dose the amount of insulin you are going to need to be as healthy as possible while receiving as little insulin as possible. And these are clearly the device of the future. Longitudinal analyses like this are going to be very, very powerful to diagnose your disease long before any medical diagnostic can be done. They will make it very easy to monitor complex disease. This will be very useful to validate new medicines. And of course, and something that is going to be, I think, a feature of the future for all of us, is to adapt our environment. Now, there is a dark side, and I think it's important to realize that there is always a dark side in science. And the thing is that in that case, you are being monitored. I cannot think of any technological progress that cannot easily be used against the people. Those having the easiest access to this progress are usually the most powerful. And the interest of the most powerful rarely coincides with the interest of normal people. You have two takes on this. One is to go Amish and to say, we reject progress and we don't want anything that has to do with progress. And it is a choice that I respect. Except that if I look back in the past 100 years, our life expectancy has kind of doubled. We are much more healthy. And in many ways, we are happier. Therefore, there was a benefit in the progress. So the question is not whether we can live without the progress. The question is whether we can make sure that the progress is made only to our benefit. And for this, there is a very easy solution, and this is called democracy. And I think we easily forget that democracy is a key progress to make sure that all the progress is used for the benefit of the people and not for the benefit of a minority. And I think that's where I want to finish. Thanks for your attention, and thanks for coming.